Oh, you're here.
Hi.
Oh, so how's it going?
Good.
Okay. Have a seat. So, yeah, I'm excited. You're excited?
Sure.
Okay. All right. Okay, I see you have your book. Can I see your book? Right. Okay. Okay, last time I asked you, last time was our first session. And how did it go? Did you like it? Oh,
It was okay.
It was okay? All right. Well, we'll make this one a little bit better than okay. Did you get a chance to take your state test that I said, the assessment test for geometry?
Yes.
Okay. And did you do it under realistic test conditions?
Yes.
Okay. So how did you do? Did you find that there are a lot of questions you couldn't do?
No.
Yeah, you probably took longer than you should have. Anyway, the idea is, okay, I think you noted how well you did, how many you got right. And so after the study sessions are over, you're going to take it again and compare and see if the study sessions helped you any, okay? And I take it that, I'm not sure, did you have time to look at the notes from the first study sessions?
Yes.
And did you have a chance to skim your book?
Mm-hmm.
Okay, good. All right. Well, we just, so I take it, so you're ready for chapter 2 of your book then, right? Okay. All right, so basically, we're going to continue where we left off. Last time, in terms of content, we were doing an overview of geometry, different things that are part of geometry. But more than that, what I was trying to do last time is to present what I consider good goals for the study sessions or any geometry course for that matter. I said I had 3 goals. One of the goals was to teach you how to take your book and read the postulates, theorems, other definitions, the sort of things that are in text boxes. I was going to work on your being able to read those things by yourself and understand what they're talking about in plain English. The second thing that I said I wanted to teach you how to do is what I call general problem solving, the ability to solve a complex problem that you haven't seen before. Most students make it through high school, even the good students, they make it through high school by memorizing different problems. And that can only get you so far. You need to be able to take basic principles and solve a question you haven't seen before. In many honor schools, what the teacher does is on the homework, they give you one type of problem, and then on the test, they twist it. These are called questions with a twist. And you get there, you say, wait a minute, we didn't study this. We didn't have anything like this. But it turns out that if you're a good general problem solver, you can take the principles you learn and solve that question with a twist. And now the third thing I wanted us to get from these study sessions is familiarity with proofs, because geometry, a lot of geometry has to do with proofs. In fact, in some courses, half the questions they ask are proof questions. It's not find the angle or find the length of the segment. It's prove that the angle is like this, or prove that the segment length is this. Okay, so those were the 3 things. And so what, let me see, the second chapter here, and a lot of geometry books, the second chapter follows the content. Their second chapter follows the content of your book. The second chapter of your book here, which is what you want me to do, has to do with reasoning. Reasoning is an important part of any geometry course. Geometry is probably of the basic high school math is the one that really places an emphasis on how you think. In geometry, they don't just want the answer. They're not just going to say calculate the degrees, the degree of angle C. Yeah, half the questions are like that, but half the questions are prove that the number of degrees of angle C is 30 degrees. Okay, so geometry really emphasizes logical thinking and making sure that all the steps in your thinking are clear and are justified. So, so today we're going to talk about reasoning because you have to understand reasoning and you have to appreciate reasoning if you're going to do well in geometry. And in fact, a good grasp of sound logical reasoning will help you not just in geometry, but when you do Algebra 2 and calculus and other higher math courses. In fact, not just in math, but even in writing. One of the things that makes a good technical writer is being very sound and clear and making the connections in your writing as you go from point A to point B to point C, and really connecting things in a sound, logical, consistent way. Basically, argumentary writing. I can tell you that many years ago when I used to write reports, my style was argumentary, where I show very clearly how I got from step one, from point A to point B, from point B to point C. And a lot of people used to like that sort of writing style. So it can help you in writing, and it can help you outside of school. It can help you in just real life. For instance, a lot of the problems or bad situations that people get into is because, somebody, she said something about you. She said, she called you this. And then you go and get angry at that person without having any clear proof that the person actually said something about you or did something to you. But if you're a very sound, mathematically minded, geometrically minded person, you would, before you go and take any action, before you go and react, you would look for some sort of proof, some clear proof as to whether the person said what, whether person A said what person B claimed that person A said, before you go and jump in person A's face and create an unnecessary conflict. So it's very useful. And so having said that, let's jump into the actual material. Okay, now your book covers two general types of reasoning. One is inductive reasoning, and at some point, maybe at the break, I'm gonna write down all the stuff I just said, okay? So, intro to reasoning. I don't want to take the time now. That's very dear. So there are two types of reasoning that your book talks about. One is called inductive reasoning, and the other is called deductive reasoning. Inductive reasoning is basically making observations and drawing a conclusion from it. you can, I don't know, you can, somebody can, what would be a good, you can, basically you observe some things, and then based on the few observations you've made or the many observations you've made, you notice a pattern, and then you say, oh, this is true. You can, let's take, okay, boys and girls. Let's take 17-year-old boys and girls. You can go to any school, get the average height of, go to first school and get the average height of the seniors, girls versus boys. Okay, in the first school that you look at, the boys are taller than the girls. And in second school, boys are taller than girls on average. Third school, boys are taller than girls on average. And so you draw the conclusion that, in any school, the boys will be, 17-year-old boys will be taller than the girls. But that's not necessarily true. You can have a school, somewhere where that's not the case. And so the pattern may not necessarily hold. Okay, the problem with inductive reasoning and the conjectures and the conclusions you come to is you're never sure that there isn't one counterexample out there that can destroy your conclusion. Remember, it only takes one example for your conclusion to be false, okay? And so basically when you make that conjecture, you try to look for a counterexample. But that still isn't good enough. You can't just say, oh, because I haven't found a counterexample, then it's true. You have to use a formal proof process to prove that your inductive reasoning conclusion is correct. Okay, so you contrast that with deductive reasoning. Deductive reasoning is based on using rules, principles, theory, logical reasoning, logic to come to a conclusion. Okay, so the way inductive reasoning works is that there's already a rule that says if A, then B. Okay, if something is true, here's an example. If an entity is a person, is a living person, then let me see if an entity is a living, I'm trying to come up with something that applies to every single human being. If an entity is a living person, then it was born from two parents, okay? It was derived from two parents. If an entity is a person, then it was derived from two parents. We haven't gotten to the point of cloning single individuals yet. So you come across some guy and he says, I only had a father, I didn't have a mother. You say, well, you're a person. You're a living human being. Your statement cannot be true. We've established already through certain principles, mainly biological principles, that can't be true. Okay, so you're just using some sort of rule to make a decision or make a conclusion about a particular case. Okay, it turns out that inductive reasoning is used a lot in science, in biology. Science is about observations. And deductive reasoning is used a lot in geometry, because in geometry, what you do is you're given a certain facts, and then you use a theorem or a postulate, and then you come to a conclusion. Okay, so let's talk a little bit about inductive reasoning and patterns, and then we'll jump into deductive reasoning. Okay, so as I was saying before, inductive reasoning, I have a nice definition here for your notes. With inductive reasoning, you use observations. You use observations to identify patterns and make conclusions or conjectures. Okay? But the conjecture must be proved using deductive reasoning. Okay? And like I said, inductive reasoning is used a lot in science, okay? So used a lot in science because science is observational, okay? So here's an example. Somebody everything in science is based on observation. It's typically science is experimental. It's empirical. You observe something, you write it down, and then you try to come up with some sort of pattern. Okay, let me give you an example. You put a bunch of material in a little cup, and you put it in an oven, at a certain temperature. You leave it in there for 10 seconds, and then you take it out and you weigh it, and you see how much is burnt off. Then you put a new batch in, you put it in the oven for 20 seconds, and bring it out, see how much it's burnt off. You keep going. And so you're able to get some sort of plot of the amount that's burnt off versus the time. And, you might see that it's a straight line, that, at least for the first few attempts, you burn off the same amount per second, basically. The rate of burning is the same. And you might come to the conclusion that, yes, it's going to continue losing the same increment every time you put it longer for 10 seconds. But that's not really the case. Something can change. By the time you get to the end of the process, something might change. But, for the most part, that's how we do experimental science. Okay. So, patterns. Okay, so let's look at patterns because the ability to identify patterns is key or critical to inductive reasoning. So I'm going to look at some of the things here. And in fact, you have scratch paper, right?
Yes.
Okay, so let's see if you can identify the patterns here. We're going to take an odd number and multiply it by an even number and try to see, we're going to do a few examples and try to see if there's a pattern to it, okay? So we'll start with, take the even number 2 and multiply it by 3. Okay, what do we get? 6, right? And is that even or odd?
Even.
Okay. Now let's take another even number, another odd number, and multiply them. Let's take 4 and multiply it by 7. What do we get?
28.
Okay, is that even or odd?
Even.
Okay. So let's take a third pair. Let's take 7 and multiply it by 6, what do we get? 42, right? So far, every time we multiply an even number by an odd number, we get an even number, right? Okay, so that's a pattern, okay? And then we can make that conclusion that when an even number is multiplied by an odd number, the result is even, okay, just from the examples we've done. But to be very honest, we can't say that that's true. We have to have some sort of proof beyond just making observations, okay, for us to conclude that that's a true statement. Okay, so let me see if they have another good example of patterns. Can you think of any patterns? Can you think of any patterns? Anything that looks like it's observing a pattern, if you look at a few examples.
A triangle.
Okay.
Square.
Okay.
Pentagon and hexagon.
Okay, what's a pattern?
It increases by one side each time.
Okay. Okay. Okay, that's sort of a pattern, but we have to restructure. Basically, I guess the way I would look at it, I would say it is that somebody gives me a triangle. If somebody shows me a triangle, and then he shows me a square, and then he showed me a pentagon, and then a hexagon, what I would say is that it looks like it's possible to draw some sort of polygon that has one more, number of sides. It's one more than the number of sides that the last polygon has or had. Okay, so that's how you can set that pattern. It seems like you can always draw a polygon. You can always add one more side to the size of a polygon and come up with a new polygon. Okay, that's a pattern. That's the pattern I would see. Okay, let me give you some numbers and see if you can get the pattern. You might need use your scratch paper to figure this out. 75. I'm going to give you 3. Yeah, 75. Oh, you need a pen too. You guys are supposed to use pencil, but I only have pens. 75. 64. 53. Okay. Can you identify the pattern? Okay, so what's the pattern?
-9.
Yeah. I would actually say it's -11. Would you agree with me?
Yeah.
Okay. So, be careful. You don't want to get something wrong because of arithmetic. What about 8 a.m., 11 a.m., 2 p.m.? What's the pattern?
At 3 hours?
Yes, basically 3 hours, and then follow the clock convention. Okay. Let's do more interesting. Those were just additive patterns. Let's do more interesting patterns. 1/2, 1/4, 1/8. What's the pattern?
Divide by 2.
Okay, that's right. Let me see if there's anything else about inductive reasoning. Oh, here's a nice example. 1 plus 2, okay, 1 equals 1, right? Then 1 plus 2 equals 3. Then 1 plus 2 plus 3 equals 6. Then 1 plus 2 plus 3 plus 4 equals 10. Okay, so basically, I want to know if you see a pattern that enables us to calculate 1 plus 2 plus 3 plus all the way up to n, where n is some integer.
Get a formula?
Yeah. You look at that, you see a pattern. So if you keep adding 1, 2, 3, all the way up to n. Okay. Okay, you may or may not know this already, but it's 1/2 times n times the quantity n plus 1. And that can be proven. And we'll take a look at that after we come back from taking a break. You know, I want to take a break because I want to write up some of the things I said earlier in my introduction. And so let's take a 2-minute break, and then we'll come back to solving that particular problem, and then we'll move on to deductive reasoning. Okay?